Welcome to Mastering Solutions. In this problem, let's start again by drawing a picture of what's going on. Usually with these ones, part of the trickiest aspect to the question is just getting it set up correctly. And this one, we have air up top, of course, as always, n equals 1. Now in this one, it's tricky. Which one do you put where? So what they're saying is the chitin is right here, chitin, and then that n is equal to 1.56. They say it's embedded into tissue, so the tissue is on the bottom and the chitin's embedded in the top of it, and that n is 1.33. So now as we have the light coming in, some will be reflected off. We're going from a low 1 to a high 1.56, so we'll go like that. But now we have the high to a lower one, so we're not going to have a phase change here. So we'll have one phase change, get that, and like that. So we want to know there is constructive interference and what the longest wavelength is. So we need the equation for one phase change with constructive interference. And that equation will be the 2t is equal to m plus 1/2 times lambda over n. And this lambda over n, we've talked about it in some of the other problems, but it's important to remember that is coming from this right here. So lambda of a material is equal to the lambda in air over the n of the material, or in this case, the chitin. And that is where the lambda air over n chitin, that's why this is here to take into account. So if we solve this for the wavelength, we get the correct wavelength from that. And what m are we going to use? We talked about this on another question as well, and it's kind of confusing. So let's solve this real quick for lambda just to talk about that. So if we multiply both sides of the equation by n, we'll get 2tn is equal to m plus 1/2 times lambda. Now we can divide both sides by m 1/2. And so what we're left with is lambda is equal to 2tn over m plus 1/2. And so we want the longest possible wavelength. So to get the biggest wavelength, we need the smallest possible m because it's in the denominator. So the bit bigger the m will be, the bigger the denominator is going to be. So that will be bigger, but the smaller the overall number will be. So if this is small as possible, in this case, m is 0, that will give us the largest possible lambda. So now we can go back to this equation up here. And we're trying to solve for, let's see, what is the longest wavelength? So we'll be using this in this case. Let's rewrite it over here. So we have lambda is equal to 2 over 1/2. Now dividing by a fraction, as we've talked about so many times, is equal to multiplying by the reciprocal. So we could rewrite this to simplify it as multiplying by 2 over 1. So that goes away. So we have 4tn. And so the lambda will have 4 times the thickness. And the thickness, they said, is 80 nanometers for the thickness of the chitin. So 80 times 10 to the negative 9 meters. And multiplying by the n, and we want the n of the chitin, which they said is 1.56. So 4 times 80 nanometers times 1.56 gives us, let's make sure, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so 499 nanometers, and we could round that to basically 500 nanometers. So that is the longest possible wavelength. And then they say for that wavelength, if that were to give us reflection for a color, what color would that be? So when we look on the color spectrum, 500 gives us a blue-green color.